So, before doing little math, right. So, we have few slides on vector space. So, now we know that whatever data we have, so we have to transform any form of data, any type of data into this space, vector space, so that we can perform mathematics, we can do optimizations, and maybe our machine learning models are basically only capable of using vector space, the data which is represented in vector space, because those models are simply the mathematical steps, those are the algorithms only. So, the input must be represented in vector space. So, these are the few property of the vector space we have shown here. We are not going into that detail. You might be aware from your math courses, when you might have studied vector algebra or algebra course, you know that vector. Right, 2D and 3D, of course, you know. Then you can extend it to higher dimensions. Right, all these properties are there. So, subspaces are there. So, if you have a subset from that vector space, you can call it subspaces. We have properties, and this is very important. We have already discussed about the regularization in the previous session. So, when your data, your model is basically, you have a data and your model is overfitting. So, we do regularization. Right. So, it might be L1 regulation which can enforce sparsity, right. L2 regularization which can take care of certain type of variances, right, covariances among the dimensions. It might be any order norm. So, regularization is simply the norm, right. So, we want to basically parameters. So, basically we perform the norm on the parameters, or regularization you can call it on parameters, so that it is bounded, it is not free, right, like the value can go whatever it wants. So, it should not go very high, it should not go very low, it should be within certain range, it is bounded in some sense. So, if you say that L1 regularization if you have used, so what L1 says that sum of absolute values of all the parameters is below certain constant. So, suppose I say that you have 1 million parameters, right, and the absolute sum of all the absolute values 1 million values must be equal to 1 or less than or equal to 1. So, you know that lot of values will be 0, because the sum of 1 million elements, absolute sum, right. So, the values are all the values are positive, right, you can say they are absolute form. So, you have to sum them and your sum should come below certain constant, let constant is 1, maybe constant is 10 even, 20, 30, it does not matter. So, the values will be very small, many of the values will be 0. So, that is why L1 normalization, L1 basically norm, or you can say L1 regularization basically enforce sparsity constraint. So, many values it basically transform to 0, or you can say learn to 0, convert to 0. L2 norm, it has also the same thing, but it has little smoother curve if you plot it. So, for L1 norm, or you can say for L1 regulation, you will get a rectangular basically, in 2D you will get a rectangle diamond shape, right. So, they are crossing on the axis, by the way, rectangle, you can say corners on the axis. And if you have a L2 regularization, so we are basically controlling, or you can say minimizing the sum of squared values. So, the whatever parameter value you have, you just square all the elements and sum it, and then try to enforce that constraint, right. It should be bounded by a certain constant. So, that is we call it L2 regularization. Then higher order norm we have, you can take maybe cube of the values, then you have to say that absolute sum when you are taking cube, whenever it comes basically degree 4 sum you want to compute. So, then the negative sign basically comes to positive, right. So, that is the idea. So, we are enforcing the parameter values not to overshoot, right, not to go beyond certain limits that we might have. So, that might basically solve certain overfitting issues. and in practice we generally use it. If we have large number of parameters, regularization generally we use, right, or dropouts you have to use, right. So, here we have a theory behind, so which function you can call as a norm function or regulation function. So, it has certain properties similar to the vector spaces, it has certain property here. So, if you are interested you can go there. So, but this is the general form of the regularization. So, this is a P norm, LP norm, right. So, here you know that how can you compute it. So, that is absolute sum of absolute values of some degree, some power, that defined by the order of the norm, right. If it is 0, right, if you p equal to 0, it means that if value is greater than 0, then you have to count 1, otherwise 0. So, that is simple counting. So, 0 norm is simple counting, right. How many values are basically greater than zeros, just count it. So, generally people use in feature selection, right. So, when you do feature selection, people use L0 norm. L1 norm says that just p equal to 1, you know that the sum is this function is equivalent to sum of absolute value. If p equal to 2, what will happen? It is sum of all squared values, right, and you just take the square root because you have 1 by p and p is 2, so square root, right. So, it becomes simple Euclidean distance. So, that is why this L2 norm is also known as Euclidean norm. A real distance is computed in higher dimensional space using the Euclidean, right. You know that how can you compute distance between 2 points. So, here one point is origin, you can say origin of the coordinate system, and the other point is denoted by this vector x vector here. You can compute the norm, and the same thing is true for the tensors or higher dimension vectors. For example, you have a matrix, so how can you compute the L2 norm of a matrix? You know that you just sum all the values, right, in the matrix, squared sum. So, that is called also, you can call it the trace, or you can say L2 norm, or you can say L2 regularization, or you can say Frobenius norm. This is very popular norm, right. When we do dimensional regression, we generally use it. So, this is a generic L1, L2, L infinite norm. You can say if someone says that in what is L in p equal to infinite. So, if p is infinite, so it says that out of all possible whatever element you have, vector element you have, just compute the max. So, max of all the absolute values in the vector is called infinite norm, or you can say L infinite regularization. So, we want to basically if you use this term in the objective function of any loss function that you have, and you want to minimize it. So, if you minimize it, you know that what will happen if your vector length is very huge, the value m is very large, m is 1 million or 10 million, right, or 1000, 10,000. So, the values will be very small, right. So, they will be bounded, and this will basically prevent our model from overfitting, from learning the data itself, right. So, this is the regularization, you can say. Then many times what happen, you might not get good accuracy in the present vector space where you have basically projected your data, original data. So, idea is can we project it into higher dimensions. So, maybe maybe next one you can you see here. So, you have this example here. So, data is simply on one axis, you can say this is 1D data, and suppose you are not able to get any classifier, maybe good classifier or linear classifier suppose. So, what you do, you just map this data to higher dimension, and in that higher dimension you just try to see that is there any linear model exist. If it exists, then your job is done, you just fit that model, linear model, in that space. Then you just transform that model into original space. So, in original space your model look like a nonlinear structure. So, a linear model in higher dimension, you can call it linear hyperplane. If you reduce the dimension, right, if you map it back to the original dimension, low dimension, it becomes nonlinear. you can see. So, we will show through example, and that is called kernel trick or you can say kernel method. Most of the few basically models, machine learning models like support vector machine and kernel PCA, right. So, they use this basically dimension enhancing technique, you can say. We call it basically mapping into the higher dimensional spaces, and those spaces we generally called Hilbert space. That is also a vector space, but we are increasing the dimension in the hope that we can get a linear classifier. So, primarily we have developed linear models, but because the data is now linearly separable or fit the has nonlinearity. So, the idea is you increase the dimension of the input data, try to fit the linear model there in that dimension, in that vector space. Once you get a better model there, just come back again to the original space. Your model, when your model from higher dimension, you are transforming it to lower dimension, its original vector space, it becomes nonlinear. So, this is the principle behind support vector machine, kernel support vector machine, or you can say nonlinear support vector machine. So, most of the models which basically do only the binary classification, so they are basically augmented or extended using this kernel trick, right. So, they try to basically lift the data in higher dimension, fit a linear model there in that dimension or you can say in that vector space, then they just map that model to original vector space just for inferencing. So, if you map this to higher dimension, what will happen? So, let one dimension we are adding, that is x square. So, you have x is data, one dimension data we have added one more dimension. What is that? X square. So, can you see what happened here? So, now can you see that, can you get a line in this dimension, in this map dimension, which can separate two groups? Suppose here in this original dimension, so these samples, maybe these three samples belongs, or you can say x6, this one belongs to one class or and others belongs to other class, right. If you uplift it, you can see here, so maybe you can get a line here that can correctly classify, or you have certain now option to separate into many groups, right. Another one is, suppose this is the case, you have positive samples, you have negative samples. So, no linear classifier can classify here, right. We need a non-linear classifier, but your model is linear, only you have a linear model. So, how will you do it? The idea is uplift the data into higher dimension. Let from 2D we are adding one more dimension, and that dimension value is this x1 times x2. So, first feature is x1 square, first feature square, second dimension is just multiplication of original two features, third one is just a square of the second feature. So, if you do it, you can see there exists a plane in 3D, linear plane, which correctly separates these two groups. Now, the idea is you have to take this back, this linear plane that you have in this 3D to 2D, because your original data is 2D. So, we will find a basically non-linear plane here corresponding to that plane that you have in 3D. So, if you reduce the dimension here, you try to transform into the original vector space, so it becomes non-linear. So, that is the non-linear geometric classifiers, mostly the support vector machine or even kernel PCA if you are using. So, they use non-linearity, right. So, just I think we are giving you a little idea about this, why do we need optimization. So, whole story is this. So, we will show you that every classifier that we have, so we have certain objective to optimize. If you have your objective is you have defined as a loss function, your task is to minimize the loss, and neural network we try to minimize the loss. Many classifiers try to minimize the entropy loss, right. Many classifiers need to basically somehow enhance the information content like tree based classifiers, right, decision tree, random forest, right, boosting and ADA boost and many more. In probabilistic classifier like Bayesian and Bayesian, you can say we want to basically use maximum likelihood, right, to optimize. So here we are just taking one basically standard machine learning model, that is support vector machine. So how it basically works? So we are giving you just simple idea here, then we'll show you the objective function, and we'll say that this objective function is quadratic and you have to optimize it. Okay. So you are given two classes, positive class and negative class. So how the support vector machine looks like? So support vector machine basically tries to fit a linear model, right, like this one. So you have the middle one is the actual model, you can say linear model, but with certain margin. So that margin is basically the distance from the true class that you have, right, the classes that you have. So the gap between two classes, you have to draw a plane, you have to come up with a plane, identify a plane such that it has maximum margin. What is the margin? So margin is basically the distance between the two closest point, right, in different classes. And the data points which are basically on the margin line. So by the way, we call it plane and hyperplane in higher dimensions. So the data points which basically lie on this marginal plane, they are called support vectors. What we call it? Support vectors. And support vectors are the data points only, right. So just these, why we call it support vector? Because the line passing through these data points, and if you know the parameters, the slope, suppose here in this 2D you know the slope, if you know the slope of any of the line, right, other of these three planes or lines that we have here, so you can draw the line. You need slope, you need a data point through which it is passing, your job is done in 2D. Same is true for other dimensions, higher dimensions, right. So these are the marginal dashed are the marginal basically hyperplane. So they basically decides the distance or margin between two classes. So our aim is to basically maximize this distance. What's SBM does? So it basically try to get a plane, middle one, such that you have to adjust the parameter values, or you have to get the parameter values, and those are the basically slopes, or you can say the weights in the dimensions, higher dimensions, so that this margin is maximized. Okay. So you might have many such, you might see that this one, so which one is better? So this one or this one? It has a little wider margin, right? Or this one, you can see here. So which one is better? I think second one, right? So these are the equation of the plane. So linear equation. So W are the basically slopes in different dimensions. So you can call it weight also. So general equation for a linear model is W transpose x plus b equal to 0. So the main plane or model is the middle one. So that is W transpose xi plus b equal to 0. And we say that these two basically marginal planes, they are equidistant from the original plane, original boundary, and this distance be assumed as a constant and let 1. You can assume any constant, even you can say that this is constant c 10, 20, whatever you want, you can just do it. So optimization will not be affected. The optimal value of W and B, these two parameters will be identified, right. So constant doesn't matter. So just say that okay, this might be variable, or you can say just say this distance is 2 unit distance. So that's why the equation of marginal plane is W transpose xi plus b equal to plus 1 for positive class, and for negative class it is minus 1. Why it is minus 1? Because the middle plane that you have, it is W transpose xi plus b equal to 0. So anything above has a greater value, below has a negative value. So that concept you know geometrically. right. So this is basically hard margin. So we are strictly we are saying that none of the basically samples will be inside this margin plane. So this is called hard margin. So suppose I say that okay, now we can allow the boundary which are basically the data points which are very close to the marginal plane. We allow them to go inside. So see here, if you allow little maybe 2-3 samples here, so your margin becomes very huge, right. That is called basically soft margin. Soft margin you can see here. So if you allow these errors, you can say your margin becomes huge. So our aim is to maximize the margin. At the same time, we want to see that the number of samples that are going inside this margin, they must be less, they must be smaller. So what is the model? So model is getting these support vectors. Only support vectors you need to draw the plane to get the model, and prediction is done. So you have a data point, you know the W value, W vector you know, weight, you know the bias value V. You can compute the value whether it is lying below the main plane, W transpose xi plus B equal to 0, or W xi plus W transpose xi plus B is greater than equal to plus 1, or it is less than equal to minus 1. Accordingly, you can decide the class. Okay. So just compute the value. If it is either side of the plane, marginal plane, you can decide the class. So this is SPM, this is soft margin. So in hard margin, we are not allowing any sample to come inside the margin. In soft margin, we are allowing little bit, and you can gain in the margin. Right. So for hard margin, you can say this is the basically equation of the plane. So W, you know that W is the basically parameter W transpose xi plus B equal to 0 is the general linear hypothesis, right. So minimize this. So the margin can be computed. So how will you compute the distance? This margin distance. How will you compute this distance? The margin. So what is this plane is the W transpose xi plus B equal to 0, right. So what is the distance from this plane to this basically middle one, you can say, or main plane, or to the this marginal plane? Or this side, you can say this is 2 by norm of W. So norm of W decides the perpendicular, right, to the plane. So W is a basically vector perpendicular to the plane. W transpose xi plus B equal to 0 is the equation of the plane. So if you divide this distance with norm of the vector that is perpendicular to the plane, here the parameter W that we have, so you will get the equation of the margin. So W transpose W, so 2 divided by W transpose W is square root, right. Maybe I can write here only, don't worry. So this equation, maybe I can write here. So what is the equation of margin? So this margin is 2 divided by square root of this W vector transpose W. You know this one, right? You can just compute it. This is very simple math. I am not going to discuss it. So that's why I discussed the vector spaces. So in vector space, you just take any 2 points, any point, you can compute the distance from the origin. So between 2 points, you can compute the distance. If you have 1 point, you can compute the distance from the origin. If you have 2 planes, you can compute the distance between 2 planes. So here we have 2 planes. And what is the equation of the plane? So W transpose xi plus B equal to plus 1. What is the equation of second plane, marginal plane? W transpose xi plus B equal to minus 1. If you compute the distance between 2, you know that a constant difference of 2 will be there, but it is 2 divided by the norm of W, right. Is it clear to everyone? Because you know that how can you compute the distance between two planes, right? If you are not aware, you can do it, right? If you want, I can write. So suppose you have two vectors in 3D, right? Two vectors in 3D. So one is a1 x plus b1 y plus c1 g plus d1 equal to 0. So this is a plane, right? In 3D. Another plane is a2x plus b2y plus c2g. So x, y and g are the coordinates, right? Plus d2 equal to 0. So what is the distance between these two planes? So there are many ways. One way is you just compute the distance from the origin of one plane. Distance from the origin other plane is subtracted. Right? You can get the difference, right? That will decide the distance. So that is basically a1 minus a2 times x plus b1 minus b2 times y plus c1 minus c2 times g plus d1 minus d2 divided by square root of a1 minus a2 square plus b1 minus b2 square plus c1 minus c2. So here you can see that's the basically norm here. That basically defines the norm, or you can say x square plus y square plus z square. So that defines the norm. You will get the distance 2 by w transpose w, right? You just take the square root. So for a special region, square root is not required. So if you want to minimize or maximize anything, a square root of any variable or any function, so it is better you just make it square and minimize or maximize, because it might incur certain computational complexity during the optimization. So this margin we have to maximize. So this, from this you can get this formulation. So this is the inverse of the margin. So your margin, what is the margin? Margin is 2 by norm of square root of this w transpose w. So square root we are removing for time being. So what is the inverse? Inverse is w transpose w upon 2 divided by 2. So this we want to minimize. So this is basically saying that we are maximizing the margin. What is the constraint? So if you don't have any constraint, it will maximize. So all the weights might be infinite, right? It is unbounded, but we have constraint here. What is the constraint? The positive sample should be below the plane w transpose xi plus b equal to plus 1, and negative samples will be after this one, right? W transpose xi plus b equal to minus 1. So this constraint you have to put there. We want to maximize the margin. We want to identify the value of w and b such that these constraints are held, right? And we want that maximum value of that. So this is the primal equation, right? So this yi, because you have only two labels plus 1 and minus 1. So basically this is two basically constraint we put in one. So what is the constraint? For positive class, what is that? W transpose xi plus b must be greater than or equal to 1. Is it clear? For positive class, the values must be greater than this one, right? So W transpose xi plus b greater than 1. For negative class, it will W transpose xi plus b must be less than or equal to minus 1. So if you combine both, right, whether y is positive or negative, just let yi represent the label plus 1 or minus 1. So yi into W transpose xi plus b is greater than or equal to 1, it will be true for both the cases. You can see here. So let yi equal to positive plus 1. So what is the inequality? W transpose xi plus b is greater than or equal to 1. For positive class it is okay. For every sample which belongs to positive class it is okay. Let yi is negative. What will happen? So minus of W transpose xi plus b is greater than or equal to 1. You just multiply minus both the side. Inequality will get changed. What will you get? You will get W transpose xi plus b less than or equal to minus 1. So this single equation basically can derive both the basically constraint that you have. So, this is the very simplest form of the primal or you can say optimization problem. And what is the variable? So, variable is W and B, B is the bias. So, in 2D you know the intercept. So, if intercept is 0, the line will always pass through the origin. So, if you go to higher dimension, for example, even in 3D, so we have set the equation A1 x plus B1 y plus C1 z plus D1 equal to 0. So, what is D1? Right. In 2D you say that y equal to mx plus c, right. So, y equal to mx plus c, c is the intercept at the y axis, m is the slope, but when you are in 3D, so what is this d? Is it an intercept? If you say intercept, so on which axis? Y, z or x? So, that is why in vector space, instead of saying intercept, we say the distance any line. So, you just remove the concept of intercept, you just say that the distance from the origin. So, any vector that you have, you just this constant represents the distance from the origin, right. So, for example, you have a y equal to mx plus c, you can just write it a1 x1 plus b1 y1 plus c1 equal to 0. So, C1 is not exactly the intercept right now, it is the distance from the origin of this particular line. Okay. So, this is generic representation of the linear plane in vector space. So, D1 represents the distance from the origin and this is called bias. So, if this value is 0, distance from the origin is 0 for any plane in any dimension, right, then that plane is passing through the origin, right. If the plane is passing through the origin, so it means that the bias is 0. Okay. So, we need bias because we want to train a generic model. We do not know that the plane is always going to pass through the origin or it is little shifted. If you enforce that v equal to 0 before the optimization, then you will only be able to train the planes or learn the planes which passes through the origin only. So, that way we need bias, right. We want a generic model, we are not limiting that model should pass through the origin, it is not required. So, if it is the case, so during the optimization process, during the learning process, your bias will be 0, right. It will be trained, it will be updated to 0, but you do not know, right, what might be the actual generic hypothesis or generic model, basically you can say. What is the dual formulation? So, we have a primal formulation, then we have a different way Lagrangian method which basically transforms your primal to dual. So, in dual formulation we have different set of variables. In primal you have a variable w, a vector w and bias b, right. And if you have a soft margin, we have a select variable xi also. So, we will see in a moment. So, dual formulation looks like this. So, alpha is the dual variable. So, we try to basically map the primal into dual, so that one becomes the other basically maximization problem if it is minimization in primal. If you are transforming to dual, it becomes the maximization problem, and otherwise right, other way it is true. So, you just see that which one is better to solve, which one is basically more cost effective for you, which one is efficient to solve. So, both will give you the similar result, because both are the quadratic objective you have here. So, they are quadratic in variable. So, W transpose W is a quadratic, right. You have a variable vector, you are just doing this. So, W transpose, suppose W is W1 and W2, you have two values, two dimensions. So, what will the value of W1, sorry, W transpose W. So, W represented by W1, W2, two members. So, it becomes W1 square plus W2 square, right. So, you have a W1 transpose, it means you have a vector W1 and W2, another vector W1, W2, you just multiply, what will you get? W1 into W1 plus W2 into W2. So, this is squared in W. So, this is called quadratic objective function, right, and constraint are linear, right. So, it is W transpose xi plus b because your model is linear. So, W transpose xi plus b is linear. Unless until you just try to map this xi into higher dimension, it might become nonlinear. So, we will discuss that in a moment. So, just see here, if you transform it to this one, then your dual formulation looks like this, where this Q matrix is basically yi, yj, these are the label of your sample I and j, and k is the kernel. If it is linear, then there is no risk. So, this is simply xi transpose xj. But if you have a non-linear, if you want to map your data into higher dimension, and then you have to come back your model, you have to map it to the back to the original dimension, then the primal solving primal is very costly. In dual it is very simple. So, we have a function, kernel function, which can do this mapping, we call it kernel trick. So, mapping to higher dimension and then coming back to the original space is very efficiently done here. So, just you have to compute a matrix, right. So, that is here. So, we call it kernel, right, and we have a mapping also. You have a primal parameters. So, how will you compute, how will we approximate the primal variables like W and B if you are given dual variables, right. Alpha is a dual variable here. So, we have a similarities here. You can just see that if you have solved dual problem, you have minimized optimized dual problem, you can get the primal variable values. If you have solved primal variable, you might try to get the dual variables, right. So, that is there, but if you optimize primal and you optimize dual formulation, and you will get certain differences. Suppose primal you have minimized it, the value is 30, but you minimize dual objective, right. So, dual of that primal, and the value is 40. So, the difference between these two is called duality gap, right. That is because of the nature of the objective function. So, if it is not convex function, then duality gap is huge, right. So, if it is convex, duality gap is 0. So, solving either of is okay. So, only you have to see that which one is better. So, if you want to just perform a linear model, so solving primal is very easy. But if you want to solve non-linear models with higher degree polynomial kernels or Gaussian kernels, dual is faster. Because in primal what you have to do? You have to physically augment the data, augment the dimension, this xi. So, xi is now mapped to higher dimension. Then you have to optimize this primal formulation in that dimension, that escalated dimension. Then come back, whatever model you have trained in linear model there, you come back to the original space and then do the prediction. So, for non-linear case, primal is very time consuming, or you can say complex thing, but dual is simple. So, that is why you can say that in library, most of the library dual formulation is implemented, right. In sklearn, if you go to the SBM, right, linear SBM, yesterday we did one program, right. So, they use this one dual, and there are methods where people do primal and dual both in order to make it faster. So, because there is a mapping, so people are doing, and maybe sample by sample, maybe there are many optimization approaches. So, we will discuss few of them in today's session. So, you have to optimize this. Now, you have formulation. In order to get the model, what do you need? You need these W and B. So, how will you compute, how will you get this W and B? So, you have to use certain optimization algorithms, you have to use certain optimization solver. So, you can directly here, because this is a quadratic function, most of the quadratic solvers are available in CBX library, convex optimization library, you can directly use them. In Python also you have library CBX opt, in MATLAB and many languages we have. You can directly apply the just feed this particular information, xi is the data that you have, you will get these values. But in a neural network, we have different type of optimization function, loss function we have to minimize. They might be quadratic, they might not be exactly quadratic. If you add here L1 regulation on the W, you can say that at the same time we want to minimize the sum of absolute sum of W vector, right. Then it becomes L1 regularized support vector machine. if you minimize L2 norm over W at the same time, it is called L2 regularized SVM, and these are the very popular superconductor machine flavors available in packages. Right. So, this is short margin. So, in short margin just we have added the slack variable. So, we try to minimize this that they should not, many of them must not go inside this margin. We call it slack variable, by the way, psi, and you have this formulation. This formulation is again the quadratic in W, but can you see the dual formulation here? So, go to here, the dual formulation, only the constraint that we will get here. So, here we are saying that dual variable must be positive, right? It must be positive, greater than or equal to 0. Other constraints are same, but when you go to the soft margin, it says that, and C is the control parameter, you can see here, that basically controls how many samples you allow inside the margin, right. So, that controls here, control is here. So, if you increase C equal C value is high, right, you can call it cost, by the way. If C is high, so it will penalize many samples, it will say that please do not go inside the margin. Okay. If C value is very small, it will allow many of them to go inside that. So, this C parameter, you can say that is here, based on this you can say that the margin becomes wider and narrower, right. If C is very huge, C equal to very high, C value is let very large, right, 100, 200, 300, 1000. So, it acts like a hard margin. If it is very small, right, it basically tries to push many samples inside the margin. So, margin is getting wider and wider. So, that is this optimization with the soft margin. So, you have a control now, right now. So, how much generalization you want in the model in some sense, right. So, this is a dual formulation. We have steps to basically how to convert from primal to dual into this session. We will do lot of demonstration on the optimization. So, this is the way how the primal and dual primal formulation is the original formulation that we made. Then you can convert into dual formulation, and both you can see that which one you can solve fast at a faster pace. So, you have a function let minimization over x, x is the variable. These are the some constraint. Inequality constraint will be there, equality constraint might be there. And how will you convert into the dual? So, you have a Lagrangian. So, Lagrangian says that you have a two type of Lagrangian variable, lambda and nu here. For every constraint that you have in the primal, for every constraint you have to introduce one dual variable. So, here you can see how many constraints you have here. So, GIX is less than or equal to 0 for I equal to 1 to m. So, you have m constraint, right. So, for every constraint you have to introduce one Lagrangian variable, right. Then another one is basically equality constraint, and you have let p such equality constraint. So, you have to introduce another variable, we call it mu. Okay. So, then what you do? So, just take all these. So, what we do? So, you just multiply with the Lagrangian multiplier, lambda into GIXI, sum all the constraint in that. Then of course, mu I into h, mu j into hjx, you just take it up, minimize the complete one. That is the dual formulation, and these lambda i's are greater than or equal to zeros, that is called Lagrangian. We have certain condition to hold, by the way, and for equality constraint you have the multiplier that you have, Lagrangian variable that you have, it does not have any constraint on that. So, just see here it becomes this one. For every constraint you have a lambda, inequality constraint, for equality constraint you have nu j. So, we have different set of variable now, we have to identify the value of lambda i's and u j's and try to, and fx is there. So, this these variables are there, x variable is there, but somehow people try to remove, somehow deduce the formulation which is free from the primal variable. So, primal variable is x here. What are the dual variables? Dual variables are lambda i's and mu j's. So, we try to do certain mathematics here, certain arithmetics, so that you can come up with the formulation which is free from the primal variable. So, for that we have KKT conditions. So, we call it Karras-Tucker condition for getting some trying to reduce and getting the basically optimal values. So, these are the some conditions which are basically true when you have a solution, optimal solution. So, one is the stationary condition, stationarity, right. It says that the dual formulation that you have here, this one, at the optimality. So, if you compute the gradient with respect to x for this formulation with respect to the primal variable, so it must be equal to 0. I think everyone understand gradient. Okay, suppose I say that you have to minimize x square. So, what is the process? What we do? So, we compute first order derivative, we equate it to 0. Then whether you have minimized or maximized, you can go to this higher order derivative. If the value is positive or negative, accordingly you can decide. So, the first order derivative at the optimality must be equal to 0. So, that is the condition. So, in vector space we just say it stationarity, right. It says that gradient with respect to primal variable x for this Lagrangian, you can say, equal to 0, and this you can prove it here, because if you compute the gradient of left hand side. So, if you compute the gradient with respect to x at the right hand side, so gradient of fx at x star, let x star is the optimal one, so it becomes 0, and other component will also be 0, because I am just telling you what will happen with the other conditions. This is primal feasibility. You know that GIX optimal star must be less than or equal to 0 at the optimality. This is the condition you have in the primal. So, it must hold for the optimal point as well. Right. Another one is called dual feasibility. So, dual feasibility says that at the optimal point, so this Lagrangian multiplier that you have lambda must be greater than or equal to 0. Complementary slackness says that lambda times GIXI equal to 0. So, can you see here the fourth condition? Fourth condition is very important. So, lot of things you can deduce, right. So, if lambda I is strictly greater than 0, please see, it is not 0. So, it will enforce that GIXI must be equal to 0. Is it clear or not? So, for every lambda, right, for every inequality this must hold, for every I it must hold. So, if lambda is 0, then GI might get positive values, it might be 0, it might get non-zero values as well, right. So, using this constraint, if you put here, you can come up with the Lagrangian representation. So, this is the basically we have basically followed that step, KKT condition, you can come up with this formulation. So, this is just between primal and dual. So, here I am just telling you how can you optimize then. So, you have this function. So, idea is you just let this is the simple one, you have objective simple x, let it is univariate for time being. So, you have to minimize x square subject to this constraint. You know that what is the Lagrangian, is it clear? You have only one constraint, right. Just do it, the dual formulation, you know that this you have to minimize, right, fx plus this one, this component you have to minimize, right. So, you have to minimize over x, maximize over lambda by the way. Just compute the derivative of the Lagrangian, you will get this one. So, you have found that equated to 0 x equal to lambda, right. So, substitute it here, you will see here. So, this is the dual formulation. So, the problem becomes this one. So, it is free from x, right. So, dual formulation is free from x. So, in primal you are just minimizing this one x square by 2, but in dual, so minus lambda square by 2 plus lambda, and lambdas are positive greater than equal to 0. If you solve it, you will see that x equal to lambda, you will solve it, you will get the same value, right. Lambda star and x star you will get. How will you solve it? You know that you again compute the, how will you solve dual? Compute the derivative with respect to lambda, because lambda is the now parameter variable, equated to 0, lambda is equal to 1. So, using completely select the k-kit condition that you have, you can compute the value of x star. So, x star must be equal to 1. So, the optimal value of this function that you have here, the minimum value of x square by 2 such that x is greater than equal to 1 is 1, and you can, it is obvious from here, right. Because of this constraint, the minimum value is 1. Suppose this is free from the constraints, there is no constraint, what will the minimum value? 0, right. So, x star will be 0. Here because of the constraint, it is coming different, right. So, this is the process we do in the optimization, where primal and dual you have to basically perform, you have to apply the Lagrangian, and there are many methods. So, this is one of the method. This method we have told that you can use any library you might have. We call it quadratic solvers available. You can directly use them, you can get the solution in one. We just write one line code, you call that library, you will get the solution. But how is it basically performed? We see that the method that we use is called gradient descent method. So, you have a convex function. So, this is the loss function, or you can say objective function. Your function shape is convex. We will discuss a little bit about the convexity. You just remind me, maybe tomorrow we will have some time. So, we will discuss it. Right. So, idea is you just choose any random point, right, just compute value, and you just compute the gradient at that point, derivative at that point. And if it is a minimization problem, just move in the opposite direction of the gradient. Gradient is also, if you have a vector, you are plotting the loss function in vector space, so your gradient is also vector, right. So, gradient is a vector, and always the direction of the gradient is always in the direction of the basically function, in the direction in which function is going to increase. So, here you can say that if you increase the value of w, the function grows upward, right. So, what is the direction of the gradient? So, direction of the gradient will be upward if you increase the w. So, what is the negative direction of the gradient? It is just opposite. So, what we do? So, just start from the random point, take the gradient, compute the gradient at that point. Just in the negative direction of the gradient, perform a movement. You just reduce, just update the value, input value or the variable value by certain, you can say constant, or you can say with certain value. You just try to reduce it. For example, here, if we are here, right. So, this point we have chosen, this is the start point, w naught is the start point. Compute the gradient. So, what is the direction of the gradient? Right, upward. Negative direction is downward. So, in this negative gradient direction, that is gradient of L with respect to w, you just put minus sign with this. So, it becomes negative of the gradient. Just multiply it with a certain constant, some fraction or some value. So, that step, that basically increment will perform here in the w. So, just we write w, whatever w naught you have. So, w naught plus this minus of this gradient into some step size you can just define. So, step size you can define. So, generally we call it learning rate when we talk about neural network. So, just define the step size. So, this step size you can define, that might be the constant, that might be variable. We will discuss that what will happen if you have a large step size, small step size, right. So, we will see that one. So, what we do? So, see here, if you want to minimize this convex function, then if you W naught you have, so what will the W1, the first update, it will be let W1 equal to W naught minus some step size into gradient. So, that is del L by del W. So, this W1 will have a value less than W naught. So, it means that if W naught is here, W1 will be in the direction of the minima. So, you are moving towards minima. This process will keep on doing until we reach a place where this gradient is 0. You know that at the minima gradient becomes 0, that is the optimal T condition. But this is true if your function is convex. You might have a function which have a plateau region, right. So, at a plateau region gradient is 0, right, slope is 0. So there might be different places where gradient becomes 0. So, you just say that okay, at the optimum if your function is convex the gradient becomes 0. So, you can stop there, or it is not exactly 0, if you are near 0 with certain approximation you can stop, right, because getting 0 might not be feasible many times. Theoretically it is feasible because in computers you cannot represent infinite numbers, you cannot represent real numbers, right, all real numbers. So, the numbers that we represent in computers are finite. Right. Suppose I say that you are representing every variable here W and B in floating point numbers, right. Let you require 80 bits for that. So, in 80 bit how many possible numbers you can represent? You know that in binary in 80 bits you can represent only 2 power 80 possible values, but real scale that you have real numbers it is infinite. So, that is a challenge, many times you might not get 0 exactly. So, you just everywhere whenever you have a division operation or some approximation operation, so you just put certain tolerance. You say that if error is, or you can say if gradient is epsilon, right, or less than or equal to epsilon, you can stop. Epsilon might be the hyperparameter, and that you can make it very close, very small, very tiny. You can say that maybe 0.00001, right, and because number of steps will increase and decrease accordingly. If you want exactly 0, so number of steps might be very huge, right. So, suppose I ask one very simple question. Suppose you have a ground, right, you have a round ground or circular ground and radius is 1, right, 1 meter or 1 unit you can say, and from the center of the ground, so every time you have to take the half of the remaining steps, right, or whatever step you are making in the first attempt, in the second attempt you have to make the half of that. So, will you reach the boundary? So, the first step you will go to the half of the distance, right. So, you can say 0.5 unit you will move, then second it will be 0.25, then you just keep on adding it, you will never reach to the boundary in practice, in real time, because you need infinite many steps. So, 1 by 2 plus 1 by 2 square plus 1 by 2 cube. If you sum infinite such a step, then sum of the series becomes, करके देखो क्या बनता है, 1 बनेगा. Infinite step का सम करोगे, बहुत छोटा सा पजल है, right. So, it is very simple puzzle. You can see that you cannot solve, you cannot reach, right, to the boundary. So, the same thing is here. if suppose your optimization algorithm chooses half, whatever you have chosen number of step in the previous one, you are taking always the half of the previous one, it will never reach 0. So, it will reach near 0. So, that bound you have to provide. You say that okay, if it is within certain 0.001 limit, right, approximation, you can stop there. So, that is why we generally use, we should not write that you can stop when gradient is 0. So, you just say that you can stop, your algorithm should stop when gradient is less than or equal to certain 0.001, or you can say epsilon, right. Epsilon is a very small quantity. Okay, what is the time? 3:40. डेमोन्स्ट्रेशन करना शुरू कर दें, राइट. ठीक है. 5 minutes, after 5 minutes we'll start demonstration. ठीक है ना. So just see, so this is gradient descent step that we made here. So in the previous case you have a w is a parameter, here you can say that x is a parameter, you can say wt plus 1 equal to wt minus eta into gradient of this wt with respect, right. So loss of with respect to gradient of loss with respect to this one. So this is gradient descent update, you just do it for many iterations until you reach to the, your gradient becomes 0. This is one criteria. Another criteria, there is no further minimization or there is no large minimization in the function, right, loss function. So you can stop. So the many criteria you can make, and if you see that even it takes longer, so maybe you can limit with the number of iterations. So all three conditions you just put there as a stopping criteria. So in worst case it can go to maximum number of iterations that you have. So any of them is true, the algorithm will stop. Okay. So then we have stochastic gradient. So we have certain issues in the gradient descent we'll discuss. Then stochastic gradient we have, batch gradient descent we have, momentum based gradient we have, ADA grade we have, RMS prop we have. So these are basically, we try to basically somehow step size that we said that. So we try to normalize step size. We try to choose a step size which will not basically overshoot the minima. Right. So then we have ADAM optimization, right. So all these we have implementation, and we'll show in the demo session we'll show you, and maybe in tomorrow's session we can briefly discuss few things. When to choose which method, right. So we'll discuss, because there are lot of optimization algorithms in neural network, you have to choose it. During the training you have to choose the optimization. So which one will you choose? So we'll show the positive and pros and cons of all these methods, right, when to use and how to use, right, we'll discuss it. Okay, so this is very popular visualizer available in Git repository, you can just practice with it. So I have written Python code as well so for you to demonstrate. So both I will share.